Okay, so ancient Chinese geometry. Small bamboo rods used to be arranged representing the numbers 1 to 9, which were then placed in columns that represented our units known as the tens, hundreds, and thousands, and so on. The ancient Chinese numbering system dates back to the second millennium BCE. It was a decimal place value, similar to the ones used today in our class. It was the first proper number system adopted by the Chinese over 1,000 years before it was recognized in the West. It made difficult calculations more efficient and easy to do because there was an actual system in which you could represent on physical, like paper and things like that. Okay, so the abuscus, which is represented here in the photo, was used in Mesopotamia, Egypt, and Greece, uh, like earlier than China. But the first Chinese abuscus, also known as the suopan, dates back to around the 2nd century BCE and is considered a Chinese innovation. In ancient China, there used to be a strong interest in numbers and mathematical problems. Different numbers were brought to have some sort of cosmic importance. There's magic squares that, in particular, were thought to have an immense spiritual and religious importance because in each row, the column and diagonal equaled up to the same amount, which is 15, as seen in an example like 4 plus 9 plus 2 is 15, 2 plus 7 plus 6 is 15. So no matter which way you go, it would give you the same sum of 15. The Lu Shu square, in order of 3 squares with a total of 15 in each row, column, and diagonal, which dates back to the circa 650 BCE. Uh, there's a legend that Emperor Yu saw the square on the back of a turtle, and it is said to take place around 2800 BCE. However, larger magic squares with greater magical and mathematical powers started to appear, resulting in Yang Hu's elaborate magic squares, circles, and triangles in the 13th century. Yang Hui also created a triangular representation of binomial coefficients identical to the later Pascal's triangle and may have been the first to use decimal fractions in a modern form. The main focus of Chinese mathematical developed in light of the emperor's high demand for mathematically skilled officials or workers, people who work for him. A textbook known as the Juixiang Suanshu, or 9 chapters on the mathematical art, written in about 200 BCE and onward, because people kept adding onto it, by a variety of authors, became an essential tool in the education of a civil service covering hundreds of problems in particular areas such as trade, taxation, engineering, and wage payment. It was especially useful as a guide to solving equations uh, and unknown numbers from other known data, and utilizing sophisticated matrix-based methods that had not been discovered in the West until Carter Frederick Gauss rediscovered it in the turn of the 19th century, and which is known as the Gaussian elimination. So we can see pictures of the book, and I just put like an example of what one of the pages in the book looks like. Louis Hui, one of the ancient China's greatest mathematicians, wrote a lengthy analysis on the book, the 9 chapters, in 263 CE, and was one of the first mathematicians to leave roots unevaluated, providing more exact answers rather than approximations. He also developed the algorithm that is determined as the value of pi as 3.14159 using an estimate using an estimate using a regular polygon with 192 sides, as well as producing a very early form of both integral and differential calculus. We have a picture of Hui, um, and yeah, so he was the one who developed pi, which is something we use today in finding the area of circles, mainly. And yeah, the Chinese went on to solve more complicated equations with many bigger numbers than those stated in the 9 chapters. They also began to investigate more abstract mathematical topics, though usually couched in somewhat artificial, uh, practical terms, such as the Chinese remainder theorem. This method employs the remainder after dividing an unknown number by a series of smaller numbers, such as 3, 5, and 7, to find the unknown number's minimal value. I have an example of what the Chinese remainder theorem. There's an example. You can pause and watch it if you want. An approach for addressing similar issues, first proposed by Sun Tzu in the 3rd century CE and regarded one of the mathematics jewels, as was utilized by Chinese astronomers in the 6th century AD to measure planetary movements, and it still has practical applications today, such as internet cryptography. There were around 30 prominent mathematicians institutions distributed around China by 13th century, golden age of Chinese mathematics. Qin Shi, a violent and corrupt imperial administrator and warrior, was perhaps the most brilliant Chinese mathematician of his time, exploring solutions to quadratic and even cubic equations using a method of repeated approximations similar to the later devised in the West by Sir Isaac Newton in the 17th century. Qin extended his method to answer equations involving numbers to the 10th power, which was extremely difficult for mathematics at the time. I have an example of Qin Shi, and next to his picture, we can see an example of what was like a page of his journal, which is where he had most of his writings. You can see like a triangle, and he was creating a theorem on triangles and what it meant for an equilateral triangle. That's basically my take on ancient Chinese geometry. Thank you for watching. I hope you learned something new, or just like took an interest into like researching where our math comes from, because as you can see in my slideshow, there's a lot that goes into like before, like the hundreds of years and centuries were gone from like the starting point to like Isaac Newton, which is something we regularly see in schools, in our textbooks, in our physics class, but it was started hundreds of years before by a person of totally different cultures that probably weren't connected. But hope this inspires you to research more on our past and history on mathematics. Thank you.